All right, let's start off with first graphing a rational function, and then we'll go on to transforming a rational function. So let's look at this one. What's the main function here? How do you classify f of x as it is? Yeah, it's just linear. So what we're going to do is we're going to flip this function upside down. And then it becomes something known as a reciprocal function. Now, the difference between a reciprocal function and a rational function is this. Reciprocal function usually is in this form. It's 1 over f of x. This is this. Whereas a rational function is more like in this form. It's going to have something on the top and it's going to have something in the denominator, okay? This one is, okay, hold. What about now? Okay, let me try resharing it. What about now? Okay, there we go. So what I was saying is reciprocal function is in the form of 1 over f of x, whereas a rational function is in the form of f of x over g of x, okay? This one is much harder to graph than this one. This one is comparatively quite easy. So to graph this, you have to first know how to graph a reciprocal function. So let's see how that works. It's actually very simple. We've done this before as well. So to graph a reciprocal function, what you do is the easiest thing to do is you graph the parent function. So let's make a grid. And our function is 2 minus x. So we know how to graph a linear function. The y-intercept is 2. The slope is -1. It means for every 1 unit you would go down, you go 1 unit across right there. To graph a linear function, you just need 2 points. And this is f of x. Now, how do you graph g of x? So here's the thing. There are some rules to graphing reciprocal or rational functions. So wherever, right, you see this point right here, how would you classify this? What would you call this? Yes. So wherever f of x has a 0 or an x-intercept, or it's also called sometimes a root, okay? All three of these, they mean the x-intercept. Wherever f of x has a 0, 1 over f of x will have a vertical asymptote. Have a vertical asymptote. Now, why would it have a vertical asymptote? Where's this coming from? Because what we do is we flip every point, we do it 1 over the original point. Here's what I mean. So this point is 2, right? So what's going to happen is that on 1 over f of x on the reciprocal function, the x values don't change. I think this would make it very clear. So x, you have f of x, and then you have 1 over f of x. So at x value of 0, the y value is 2. Now the reciprocal function, the y value is going to be 1 over 2. You just flip it upside down. Over here, it's at 1, it's a 1, so that point is going nowhere. This point right here, when the x value is 2, the y value is 0. Now, but check this out. When we go to do 1 over 0, we get indeterminate. So that's where the vertical asymptote comes from, because we're trying to divide by a 0, okay? So from here, it's very simple. All we're going to do is we're going to flip all the points. So the 2 becomes 0.5. The 1 stays 1. Now this point becomes a vertical asymptote. Now this point is -1. I didn't write it. You don't have to write every point on the table, but this point, the y value is -1. 1 over -1 is -1, so this is going to stay unchanged. This one, the y value is 2, negative 2, it's going to become negative 0.5, just like that. And that's rule number one. Rule number two is that a reciprocal function, okay, reciprocal function again means 1 over something. A reciprocal function will always have a horizontal asymptote. Where? It's going to have a horizontal asymptote at y equals 0, also known as the x-axis. So let's put that plot down here as well. Like that. Those are going to be our two asymptotes. Now, you cannot cross the asymptotes. So what you're going to do now is try and connect the points in a way it makes sense. So obviously we're going to have to connect these 2 points. If you see the pattern, it cannot go this way because that would mean it crosses the asymptote. The only way it can go from here is it can go up. It's going to ride that asymptote. Same thing here. It's going to go down. It'll never cross the asymptote, but it'll approach 0 when x is negative infinity on that side. And on this side, it's going to look like this. Just connect the points and ride the asymptotes. And there you go. That's going to be a rational function. Did that make sense? Where did I get this point and this point? Yeah, so, okay, okay, let's check out this point, right? So again, what I did there was when the x value is, what is this? 2, 3, 4, right? What's the value of f of x? It is negative 2, right? You see this? So now how did I get that point? I did 1 over negative 2, which is negative 0.5. So that's y value there is negative 0.5. You can actually get more points. I was just being lazy. So let's put more points here just for this one question. So 1, 2, 3, just to make it, just to hammer this point home. So now when the x value is 5, right? The y value is negative 3, and now the y value would be 1 over negative 3, or like negative 0.33. So that's going to come, when you go to plot it, it's going to be slightly higher than this. You're going to get that point, yeah? And you can do the same thing on this side as well. When the x value is like 2.5, the y value appears to be negative 0.5. I'm talking about this point right now. So what's going to happen is when you flip that point, 1 over negative 0.5 is 2. So this point will come right here. So you can get an infinite number of points, in fact, if you want. Okay? But you don't need, all you need is a couple of points, and you know your asymptotes, and you're just going to connect them in a way that it does not cross the asymptote. Like, let me show you a weirder one here. Okay, we don't know what this function is. It has 1, 2, 3, 4 turning points, so it's a x power 5 function. My point is, how would we flip this? Well, let's say this is some f of x. The question will be graph 1 over f of x. So again, we're gonna stick to the rules, right? What are the rules? Whenever there's a 0, we don't know what the x value is. We don't really care. Whenever there's a 0 on the parent function, on the reciprocal function, what are you gonna have? Vertical asymptotes. Rule number 1. What's the next rule? It has something to do with horizontal asymptotes. There's always, for a reciprocal function at least, not necessarily for a rational function. For a rational function, we have to do like the y value ratio test. But for a reciprocal function, you'll always have an asymptote there. Now look at this, okay? We're going to flip the entirety. This is some value, let's say 5, 6. It's going to become a very small number. Ones always stay as ones. So they're the best. So that's a y value of 1, that's a y value of 1. This, I brought it down here. Now look at this. The only way this is going to work is if you connect it in this fashion. Because again, you're not allowed to cross those asymptotes, right? Even here, look at this. This point is some 5, -5. It's gonna become like less than 1, so it's gonna jump here. The ones and negative ones on the y, the 1 and -1 y values always stay where they are. So that's what this is, and that's what this is. That point comes from flipping this. Now you connect it, you'll see that there's only one way this is gonna work. It's gonna look like that. And you see the pattern, right? Here it's gonna be like this. Here it's gonna be like this. Here it's gonna be, again, the 1 stays where it is. This point is a very large y value. It's gonna become a very small y value because we're doing 1 over it. So on this section you have this. And then finally on this section down here, the y value of -1 stays where it is. Now, again, here you cannot go in this fashion, right? That shape doesn't make sense. The only shape that makes sense here, if you think about it, you have two shapes. This is the one. Because again, you cannot cross the asymptotes. Then you write it all the way down. There you go. That could be like a 2-point question. No equation, no nothing. Just straight up flip this function upside down. And you're just going to stick to the 2 rules. And it's not that difficult. The third rule is obvious. I didn't write it down, but the third rule would technically be the ones and -1s always stay stagnant. They don't move. Okay? The ones and -1s, they always stay exactly where they are. That one's a bit simpler. Is it? No, this one I don't know. They made it look difficult, so I guess let's do this one. Okay, what type of a function do we have? Quadratic. How do we graph this? Is this a difficult function to graph? How would you go about graphing this? It's a simple quadratic. We factor it? I don't think we even need to factor it. So think about it. X squared is this. Think about the transformations as happened. -x squared is this. And then it just goes up 9 units, right? So it'll look like this. That has a y-intercept at 9. And it'll go like this. What's going to be the x-intercept? It'll be 3 and -3. Yeah, exactly 3. There you go. That's quadratic done. I want to make it look a bit better though, because we're going to flip this. To go to y value of 9. Right. Cool, let's start graphing this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we need to go there. That's our vertex. And our x-intercepts are down here, -3. Down here, +3. Let's connect them. We goes down. We and then go through the x-intercept. Okay, yeah. And then goes down. So that's good. Okay, now what we're gonna do is we're gonna flip this. How do we flip this function? What's rule number 1? Think about vertical asymptotes. Where would it have vertical asymptotes? Yeah, exactly. So perfect. So step number 1, always just graph the vertical asymptotes. So there's gonna be one here. It's an invisible barrier. There's gonna be one here. Okay, what's the next rule? Yes. Yes. So which is the x-axis, right? So now we have this as well. So now all we're gonna do is flip this, okay? All we're gonna do is flip this. And I'm gonna be a bit lazy about it. So the one point though you can't be lazy about is the y-intercept. So that point is 9. What does that point become on the reciprocal function? So this is what I mean. So right now at x equals 0, f of x, the y value, the y-intercept is 9, right? On the flipped function, what does that point become? And again, it's easier than you think. All you do is you do 1 over it, right? Look at this. Becomes 1, 9. 1 over 9. You get that? So that's the only point that people look for. Everything else you can just sketch it by hand. So I'm just gonna say this point is this 1 over 9, okay? And then our stagnant points, 1 and -1. So 1, y value of 1 will always stay there. Y value of -1 down here will always stay there as well. So that's good enough for me. So now all I'm gonna do is I'm gonna connect the points, and you see that there's only one way this is gonna work. You come from here through this y-intercept, go through this. It'll look like a U. I crossed the intercept there, but yeah, like that. Then down here, right, you'll see that only one shape will make sense. I'm talking about shapes. I'm talking about there's 4 options. Why don't you tell me? Okay, we're looking at this section. Which shape would make sense? A, B, um, what else can I draw? C, D. Which shape would make sense here? B is the only one that makes sense. The other ones don't make any sense. So we're gonna go B here. What about on the other side? Yeah, it's the same, just flipped. So it's kind of would look like D. There we go. And that's as good as it gets. That's perfect. We'll briefly talk about some of these other things here. So I'll just make a table here. I guess we can say f of x, and then we can say the reciprocal function 1 over f of x, and we'll just answer some of these questions here. So let's start off with the domain and range. What's the domain of f of x? Yep, what's the range of f of x? Yes, y has to be, same thing. What's the domain of 1 over f of x? Yes. So when we're talking about domain, right? Domain, it doesn't really apply to this, but what you do is you set denominator equals 0, okay? And then this will give you the restrictions. So if you do that here, it gives you the x-intercept plus minus 3. So that's your domain. X cannot be plus minus 3, okay? What about the range? Yes, that's the only restriction. Okay, positive, negative intervals. So where is f of x positive? It means the y values we're talking about. For which x values are the y values positive? So if you look at the quadratic, where is it positive? Yes, so between -3 and 3. And it's negative between -infinity to -3 and from 3 to positive infinity, right? Yeah. So that's where it's negative. Like this section down here is this, and then this section down here is this. 3 to positive infinity. This is interval notation. What about for the flipped function, what are the positive and negative intervals? Do they change? What do you think? Would the positive and the negative intervals change for the flipped function? They don't. It's literally the same thing. So that's another important characteristics about reciprocal functions. The positive and the negative intervals, they do not change. They're exactly the same. So you don't even have to graph the reciprocal if this is the only question. Okay, let's now talk about increasing and decreasing. Where is the quadratic increasing? And when I say increasing, right, we're talking about slope of the tangent line. When is the slope of the tangent line positive? So what you can do is I'm looking at the quadratic, you can start drawing it. You see it's positive, 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 zero, negative, 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 negative. So where is the slope of the tangent line for the quadratic positive? No, no, for the OG, for the quadratic. Or yes. And it's decreasing when x is greater than zero, right? What about for the reciprocal function? Now we're talking about the flipped. When is that increasing? When is the slope of the tangent for the reciprocal function increasing? Yes, but not quite. Everywhere greater than zero? Does the function jump anywhere? Is there a discontinuity? At three. So the function's gonna increase everywhere when x is greater than zero, bar x cannot be three. It's gonna decrease when x is less than zero, except there's like a discontinuity, x cannot be negative three. So increasing, decreasing intervals, they're not the same. Positive, negative intervals are, increasing, decreasing intervals are not, but they're related. The increasing here becomes the decreasing here, and then with restrictions, if there are any discontinuities. The decreasing interval here for the parent function becomes the increasing function here. Again, you gotta mention the discontinuities, which in this case are your vertical asymptotes. If there were holes, we would also mention the holes. And that's it for this question as well. So this is as good as it gets. I think if you can do this question that we just did, this is as hard as it gets for like graphing a reciprocal function. Like, let's do an even harder one. Like, let's look at this, okay? We're gonna graph the sine function. Sine function starts at the origin. And then at 90 degrees, quarter period, a full period is 360 degrees. At 90 degrees, it comes to 1. That's the maximum. And then another quarter period, it comes back down to the midpoint. And then another quarter period, it goes down to the minimum. And then one more quarter period that finishes the cycle, it comes right back up. So this is the plot of sine x. It's a periodic function. It's a trig function. What we can do is you can extrapolate now that you have one cycle. It's not gonna be perfect, but just bear with me here. It's terrible, whatever. We'll just stick with this. Maybe I'll give it a little bit more here. Okay, yeah, let's stick with this. Now the question is flip it, okay? The question is this. Flip, when I say flip, I mean graph the reciprocal function. One cycle of sine x. So one cycle of sine x is what we just graphed from here to here. 360 degrees is one cycle, one period. Okay. How do we do this? Is this difficult? Do we need to do anything new to do this? No, it's the same rules. Whenever there are zeros, graph your vertical asymptote. So right there, right here, right here. For a reciprocal function, by the way, we're trying to graph 1 over sine x. Do you remember what this is called? It's a function of itself. What's 1 over sine x? I'll give you a hint. It's one of the secondary trig ratios. It's not SOHCAHTOA, but it's one of the secondary ones. You remember the secondary trig ratios? Cosecant, secant, cotangent. These are the secondary trig ratios. These are basically the primary ratios flipped. 1 over sine is cosecant. 1 over cos is secant. And 1 over tan is cotangent, okay? So when it says flip one cycle of sine x, it's asking you to graph this function, which is actually, they're asking you to graph cosecant x without actually telling you to graph cosecant x. So anyways, let's go back to flipping this. It's not that difficult at all. So we have the vertical asymptotes. Let's give it a horizontal asymptote. And now these are the stationary points. They don't move because the y value of 1 and -1. What else do we need? We have pretty much everything. I will give you some mini points though here, because I feel like we're gonna need it here. So we're gonna do 0.5s here. So right now, the y value here is 0.5. Okay, when you flip this, what's the new y value? This is what I'm saying. Right now, we don't really care what the x value is. We know the y value there is 0.5. When we flip it, what does that y value become? 2. So that point is gonna jump somewhere here. Same thing here, 0.5 is gonna jump somewhere here. And now I'm gonna connect it with my y value of 1 and then write the asymptote like that. Same idea here. Now we're negative 0.5, it becomes -2. And then you have your stagnant point there, y value of 1, it never changes, stationary. Then you just, there you go, that's one cycle. It would look exactly the same here as well. So there would be a vertical asymptote here. It'll look like this here, it'll look like that there. And that's the graph of cosecant x. Very simple, right? So they might not teach you. In fact, your teacher may never show you what cosecant x looks like, but you will know what sine x looks like, and definitely they can ask you to flip sine x. And again, as you can see, it's not the end of the world. It's actually quite simple. Let's see what else we can do. Where are the radicals at? Okay, we're gonna graph this function. So what kind of a function do we have here? Okay. Will this have a horizontal asymptote on the x-axis? Right? So now that's something we need to decipher. So for rational functions, the rules are a little bit different. Well, the zero rule, vertical asymptote rule is the same. The rule number one is the same. Zero becomes a VA. But here's what you should consider for a rational function. Okay, I'm going to give you a new set of rules. For a rational function, what you should do is always try and see if you can reduce it, if possible. Like here, is this reducible? No, it's not. So this is as far as it gets. But if you get something like this, is that reducible? Yes, it is. Because then that becomes x plus 3, x minus 3, x plus 3, right? This and this cancels out. If something cancels out like this in a rational function, like this is a hole in the curve. The hole right now is going to be at x equals negative 3. So you said that whatever you canceled out, it has nothing to do with this. The hole would be at x equals negative 3. It has everything to do with what you just canceled out. And you said that equal to 0. So for a rational function, just check to see if there are holes by reducing it. This one, there's no point. We can't reduce it any further. Now here's the more complicated thing about rational functions. Horizontal asymptote, there are rules, and you're going to have to memorize the rules. So for horizontal asymptote, there are three cases. So case one, again, you have rational function will always be f of x over g of x. If the degree in the numerator is less than the degree in the denominator, an example will be this. The degree in the numerator is 2, the degree in the denominator is 3. If this happens, you have a horizontal asymptote at y equals 0, same as the reciprocal function. If the degree in the numerator is equal to degree in the denominator, which is what we have in this case, so the horizontal asymptote is going to be at y equals, okay, check this out, it's going to be at y equals the leading coefficient of the numerator divided by the leading coefficient of denominator. Let me just quickly run you by what in the world is a leading coefficient. It's actually a very simple idea to understand. I just need some functions here. All right, look at this. Linear function, leading coefficient is 1. Leading coefficient is 3. It's the number attached to the degree term. Leading coefficient is 1. Leading coefficient is 4. 1, 2. You see that? Leading coefficient is a number that's attached to the degree term. What's the leading coefficient here? Perfect, yes. So that's what I mean here. So in this case, because we have case number 2, the horizontal asymptote is going to be at 3 at y equals, okay, y equals 3 is the leading coefficient in the numerator over 1, 3. That's case number 2, if the degrees are the same. Case number 3 is the hardest case, where the degree in the numerator is bigger than the degree in the denominator. When this happens, there are no horizontal asymptotes. Example. If this happens, no horizontal asymptotes, but you have another unique asymptote. This is called an oblique asymptote. Let me show you an oblique asymptote looks like. So I'm just gonna put this function on Desmos. Desmos doesn't show you asymptotes, but you can kind of infer. So check out this function. Is this right? Can x be 0? Yes, it can. Oh, it looks good. Looks good. Looks very wonky though, like that. So a leading coefficient is always going to be slanted. In this, you can see the curves themselves are a bit slanted. Maybe if I add a number here, it'll look a bit better. So just give me a sec. Plus x minus 8, maybe. Okay, something like this. Whenever the degree in the numerator is higher than the degree in the denominator, your graph itself will be slanted. And you can draw a line through it. You can draw a straight line through it. And the straight line portion, okay, the asymptote itself, it comes from long division. You remember long division? You can also do synthetic. Synthetic, though, would you be able to do, I don't know if you remember, pop quiz. Can you do synthetic division here? How much do you? Yeah, can you do it? Is it? Ah, cool. So you can't. Synthetic division requires you to have a linear divisor. So in this case, the only thing that works is an oblique asymptote. So there you go. That's probably the hardest thing about a rational function is deciphering what the asymptotes are. Once that's done, it's the same rules as the reciprocal function. So now actually let's go about graphing this. So obviously we can't reduce this, right? So what we're going to look for is the vertical asymptote and the horizontal asymptote. And it's easier than you think. For vertical asymptote, you're going to set the denominator equal to 0. Where's the vertical asymptote for this? -2. And then we're not going to be super duper. Oh my God, my pen is. Okay, there we go. So at -2, x equals -2, we're going to have a vertical asymptote. There we go. Where's the horizontal asymptote? 3 at y equals 3. So 1, 2, 3, we have these. So that's step number 1. Okay, step number 2, we're going to find the intercepts. And again, both of them are easier than you think. For x-intercept, you're going to set numerator to 0. Where's the x-intercept? At 5/3, which is what, 1.67, right? 1.666. So 1, 2, so let's say it's right here. So that's your x-intercept of 5/3. What about y-intercept? To find the y-intercept, you set all the x values inside the function equal to 0. So this set to 0, this set to 0. What do you get? You get -5/2, which is what? -2.5, right? So there you go. That's going to be your y-intercept. So these things, if you can remember them, would help you go far for rational functions. And again, it's not that difficult. Like these are just logical. We've been doing this for any function. If you think about how we find the x-intercept, we literally set it to 0. How do you find the y-intercept? You set all the x values equal to 0. That's nothing new. Okay, so let's graph those as well. So -2.5, 1 to 2.5 would be down there. And do you see the pattern? How this could possibly look like? I'm just looking at this point and this point, right? There's only one way this is going to work, and it's this. Do you agree? There's nothing else that's going to work here. So We, and then write it. Now the question is, are we done? No, we're not. Okay? No, we're not. So I'm calling these, this is my own lingo here. I'm calling these sections. So you have one section here, you have one section here. The number of sections is always vertical asymptote plus one. So what I mean by this is this graph will have two sections. We have one of them. It has another section to the other side of the vertical asymptote. So in this case, we have one vertical asymptote, so the total number of sections is two. Now, for the other side of the vertical asymptote, by the way, we can't be up here. Can you tell me quickly why we can't be up here? The other section can't be up there, and it has something to do with it being a function. What would happen if the other side was up here? Let's say it looked like this. What does this mean about f of x? Is it a function? Does it pass the vertical line test? No. So f of x cannot, the other section cannot be up there. So now you have two options. Is it here or is it here? Do we know yet? We don't. How do you think we can decipher where it is? And it's a very basic method. I'll give you a hint. The x value here is -2. So what we could do is maybe plug -3 in there to see what the y value is. So if the y value is less than 3, we're here, right? And then our curve will look like this. If the y value is more than 3, we know we're in the top section and our curve will look like this. So let's plug the y value of -3. So -3. So 3 times -3 minus 5 over -3 plus 2. It's quick maths, negative 14, -1, 14. So the y value is 14 at -3. What does that tell us? Are we in the bottom section here? Are we in the top? The top. So the y value of 14, let's just arbitrarily pick this. This is 14. Do you see what the curve should look like up there using just that one point and the asymptotes? You don't need more than 1 point. So you just need to know the asymptotes. You need to know that you cannot cross the asymptote. There's only one shape that's going to work there, and it's this. Do you agree? You're done. Because when you think about it, you have four shapes. This is not going to work because it's going to cross through that asymptote. This is not going to work because it's going to cross through that asymptote. So you're limited to this and this. This is also not going to work. There's only four shapes, right? And two of them are just like reflections. Like this one is just a reflection of this. This one's just a reflection of that. So basically there's two shapes and you can always pinpoint which one it is. And there you go. That's what the curve should look like. And that's your rational function. Did that make sense? Hopefully you did. It's not terribly difficult, right? Just remember these things for rational functions. If you can remember these, you're set. And sometimes you have to do this as well. This is very important because you don't know where it is, right? We don't have enough information. So all you have to do is plug in a point and then that will tell you, that'll open up everything you need for that function. Before we go further, I feel like we should learn division. Where was this division? I'm going to show you synthetic division in case we run into like an oblique asymptote. I know we've done this, so it'll just once I show you how to do one, you'll remember how to do all. So let's say this was the question. We're dividing the top function by the bottom function. Why? Why would we want to do this? Think about the horizontal asymptotes. What do you think the purpose of doing this is? What's the degree in the numerator? So right now this is the numerator because it's f of x over g of x, and this is the denominator. What's the degree in the numerator? What's the degree in the denominator? 1. When the degree in the numerator is bigger than the degree in the denominator, right? You have an oblique asymptote. You don't have a horizontal asymptote anymore. You still have a vertical asymptote at +3, but you no longer have a horizontal asymptote. You have something called an oblique asymptote. Oblique asymptote can be linear, can be quadratic. In this case, if you see it, when you do 3/1, the asymptote itself is going to be quadratic. So it could be something like this. Because we have one vertical asymptote, there'll be two sections. Okay. So the curve for this could possibly look like this. I don't know what it looks like. We have to plug in some points and check. But this could be one example. So that's what it'll look like if there's an quadratic oblique asymptote. But basically my whole point is you want to do long division sometimes because you may have a degree in the numerator that's larger. So to see your oblique asymptote, there's no other way. So let's first show you using the traditional method of long division. This is called I'm calling it the divisor. This is called the dividend with a D. Whenever you're putting this inside of this box, make sure none of the degrees are missing. If any of the degrees are missing, you're going to put that as plus 0x. We don't have to in this case because we have 3, 2, 1, 0. But if it is missing, this applies to both synthetic division and long division. You're going to put a plus 0x. All right. So now the way to do this is step number 1. X times something is 3x cubed. In other words, that something, this is going to be your quotient. The somethings are always your quotient. The quotient is going to be 3x cubed over x. In other words, 3x squared. So look at this. We have 3x cubed here. We have x here. We need to multiply by x with something to get 3x cubed. The only thing that works is a 3x squared. That's step number 1. And then once you have the quotient up there, you're going to multiply the quotient with your divisor, with the entirety of your divisor. 3x squared times x, 3x cubed. 3x squared minus 3 times that will be minus 9x squared. And again, we're doing long division, so subtract. This cancels out. This becomes a plus. -5 plus 9 is 4. Once you cancel something, you're allowed to bring the next guy down. Again, rinse and repeat. X times something is 4x squared. What is it? 4x, so positive 4x. So plus 4x, and then you're going to multiply 4x with the entirety of the divisor. So that's going to be 4x squared minus 12x. Long division, we subtract. This cancels out. Negative, this becomes a plus. So now you have 5x left over. We cancel something. We're allowed to bring the next guy down. -1. Okay, x times something is 5x. What is it? 5. Minus, this cancels out. This becomes a plus 14. So now this is your remainder. If there's a remainder, that means it's not a factor. Keep that in mind. We'll talk more about it next time. But that's your remainder. The remainder ideally should be 0. Then you have a good function you can graph. If your remainder is 14, you will not be able to graph it, unfortunately. The next thing you need is the quotient. This is your quotient because you can't find the x-intercepts. That's the issue. If the remainder is not 0, you won't be able to find the x-intercepts. It's going to be kind of hard to graph this. And that's the only thing you need. Quotient and remainder, right? So this is doing it long division. If the divisor is linear, If the divisor is linear, what you can do is instead of doing long division, you can do synthetic division. But again, remember, this only works if the divisor is linear. If it's quadratic, then you have to do, or up, you have to do long division. So here's how you set up synthetic division. X minus D, okay, you're going to compare it with X minus K. The K is your divisor. What's the K value here? Compare these two. 3. So that 3 comes all the way outside. And here, these guys, your dividend, you're only interested in the coefficients. So 3x cubed 3, -5, -7, -1. And again, if something is missing, then you put that as 0. But in this case, nothing is missing. All the degrees are lined up perfectly, 1 of 3 to 1, 0. So, like that. Okay, step number 1 in synthetic division. This number, you see this number? Always comes down as it is. And in synthetic division, we add, we do not subtract. So bring down the first number, that's a 3. And then what you do is you multiply 3 with your divisor. So that's a 9. Now you add -5 plus 9 is a 4. Again, you multiply this with your divisor. 4 times 3 is a 12. You add, you get a 5. What's the number here? 15. Your remainder is 14, and we know that remainder was 14. So now this is your quotient, but you have to be able to read this because we're doing x cubed over x, right? That means the first term here must be x squared. The next term must be x. The next term is just your number 5, the constant. So this is the important part in synthetic, that it doesn't give you technically the power, but you can easily decipher it by doing this over this. Leading coefficient, the degree of the top over the degree of the bottom. I guess that's what I'm trying to say. 3x squared. There you go. Synthetic division, much easier. When would you do this? You would do this when you're trying to find a rational function and the degree in the numerator is bigger than the degree in the denominator. In that case, you know there's no horizontal asymptote and you would get a oblique asymptote. Did that make sense? Okay, cool. Let's call it there for today. See ya.